Welcome to the Deep Dive, the place where we take the most revolutionary ideas in science, really dig into the sources, and pull out what you absolutely need to know.
And today we're tackling something huge. A theory so ambitious, it challenges the very foundation of how we understand gravity.
Yeah, this cumulus framework holds up. It means gravity. The force that, holds galaxies together and keeps our feet on the ground isn't fundamental at all.
We're diving straight into that massive rift in 20th century physics. It's been over 100 years, right? And we're still stuck with these two incredible but ultimately incompatible pillars describing reality.
On one side, you've got Einstein's general relativity, GR, beautiful description of the big stuff planets, galaxies, the universe treating gravity as geometry, the shape of space-time.
And on the other, quantum mechanics, QM, the rule book for the tiny stuff particles, fields, all that weird quantum behavior like entanglement.
And the problem is, they just won't play nice together. They describe different scales magnificently, but try to use them together.
It breaks down completely. The incompatibility is deep, structurally deep. When physicists try to quantize gravity, like treat it with particles, maybe a graviton.
Which is hypothetical anyway.
Right, hypothetical. The math just explodes. You get these infinities that you can't just brush under the rug like in other quantum theories. Non-renormalizable infinities. It basically means the combined theory makes no sense mathematically.
And it's not just a blackboard problem, is it? This failure has led us straight into what people call the dark universe crisis.
Oh, absolutely. It's a huge embarrassment for cosmology. Because GR, our best theory of gravity, can't explain what we actually see out there.
Yeah.
Well, we've had to invent placeholders.
Dark matter and dark energy.
Exactly. Labels for stuff that makes up, 95% of the universe's energy and mass. We're saying most of reality is dark, unknown, just because our gravity equation doesn't work right beyond our local neighborhood, basically.
So our sources paint this Q idea as a really radical way out. It flips the script. Instead of trying to force gravity into a quantum box.
What if gravity isn't fundamental to be quantized? What if it just emerges, like temperature emerges from the jiggling of atoms? It's not a property of one atom, but of the collective.
So gravity could be an emergent property of the quantum vacuum itself. That's pretty mind-bending.
It is. And that's our mission for this deep dive. We want to unpack that core philosophical shift, space-time, as information, basically. Then we'll get into the math, this proposed Qmn, break down its parts.
And crucially, the tests. How they plan to prove it or break it, using data from the cosmos, from galaxies, even from lab experiments.
Right. It's radical, but it makes concrete, testable predictions right now. That's the exciting part.
Okay, let's make sure we really get the scale of the problem first. This structural incompatibility between GR and QM, what's at the heart of it, mathematically?
Well, GR is all about smooth geometry. Its bedrock principles are things like general covariance physics looks the same no matter how you map it, and critically, the Bianchi identities.
Those ensure energy and momentum are conserved, right? Tied to the stress energy tensor.
Exactly. It's all geometry, curvature, defined by the metric tensor. Very elegant, very classical in a sense.
But QM is not smooth.
Yeah.
It's fuzzy, probabilistic.
Totally different language. QM uses operators, probabilities, wave functions. It talks about fields constantly fluctuating, virtual particles popping in and out of existence, tools like Green's functions, Feynman path integrals. It's a quantum world.
And you try to overlay that fuzziness onto GR's smooth background?
Chaos. The gravitational force is incredibly weak at quantum scales, and when you calculate the effects of all those quantum fluctuations on space-time, boom, infinities again. And the usual tricks, renormalization, they just don't work for gravity. The structure fundamentally resists quantization.
Which brings us back to the cosmos and those embarrassing gaps in our understanding.
Yeah.
Like a dark matter problem.
Yeah, the dark matter dilemma. It's purely observational. Astronomers look at spiral galaxies, they measure the light, estimate the mass of all the stars, and guess the normal baryonic stuff.
And then they use GR to predict how fast the outer stars should be orbiting.
And the prediction fails spectacularly. The outer stars should slow down or even fly off, but they don't. Their rotation curves are flat. They're moving way too fast.
So GR says the galaxy shouldn't hold together, but it obviously does.
Right. So to save GR, we say, there must be this huge invisible halo of something else. Dark matter, providing extra gravity.
A fudge factor, basically.
Essentially, yeah. A necessary one to make the equations match what we see. But we still have no idea what it is.
And then there's dark energy,
yeah,
which is connected to the cosmological constant problem, you call that the biggest failure in theoretical physics.
It's hard to overstate it, yeah. Dark energy is the name we give to whatever is causing the universe's expansion to accelerate. That was a huge surprise discovery.
Okay.
Theoretically, the most natural candidate for this energy is the energy of empty space itself, the quantum vacuum energy. Quantum field theory predicts the vacuum isn't empty, it's fizzing with energy.
Right, so you calculate that energy.
And you get a number that is catastrophically, absurdly wrong.
How wrong?
Predicted vacuum energy density is bigger than the observed cosmological constant, the thing driving the acceleration, by, well, estimates vary, but it's something like 1020 times, a 1 with 120 zeros after it.
That's incomprehensible.
It is. It's like predicting an electron weighs more than the observable universe. It signals a fundamental breakdown in our understanding of gravity, the vacuum, or both.
And this already massive problem got even worse recently with the Hubble tension. Why is that such a big deal?
The Hubble tension is like the universe screaming that our model is wrong, or at least incomplete. We have two really good ways to measure how fast the universe is expanding right now. The Hubble constant?
Method builders.
Okay, method one.
Look at the early universe, the cosmic microwave background, the CMB. The patterns in that light, measured brilliantly by Planck and other probes, let us calculate what Tₘₙ should be today, assuming our standard cosmological model, lambda CDM, is correct.
Do it too. Measure it directly, locally. Use things like supernovae and Cepheid variable stars, standard candles, to build up a distance ladder and measure the expansion rate in the nearby late-time universe.
And they don't match.
They persistently, stubbornly disagree by about 8 or 9%. And the error bars have shrunk to the point where it's very unlikely to be just a measurement mistake.
So what does that imply?
It strongly suggests something is missing or wrong in our standard model. Either our picture of the very early universe needs tweaking, or, and this is where Qmnu gets really interested, gravity itself, or the energy content of the universe behaves differently at different times or on different scales.
A dynamic gravity.
Yeah.
Not just Einstein's constant G.
Potentially, yes. The tension basically demands some kind of new physics that changes the expansion history between the early universe and today.
Okay, so the standard picture is creaking under the weight of infinities. Dark stuff we can't find, and these contradictory measurements. Qmnu comes along and says, maybe the problem isn't the details, maybe it's the whole foundation. Gravity isn't fundamental, it emerges from entanglement. How do we even start to think like that?
It's a massive mental shift, absolutely. You have to stop thinking of space-time as this pre-existing stage, this fixed background geometry that things happen on.
Right.
Instead, Qmnu proposes space-time itself is the emergent phenomenon. Like, think about wetness. Wetness isn't a property of a single H2O molecule, right? It emerges from how lots of them interact.
Okay, I get the analogy. So space-time emerges from what?
From quantum information, specifically from the entanglement patterns of the fundamental constituents of the vacuum, whatever they are. It's like space-time is woven from threads of quantum connection.
The universe as a giant quantum information processor. And gravity is like a feature of the processing. That's not a bad way to put it. The theory lays out some core principles. First, the quantum informational principle. Reality at its base is some kind of quantum information structure. Think of it like a graph, gamma, that exists before geometry. Information first, space and time second. Wow. Yeah. Then, the entanglement-driven emergence principle. Space-time geometry, curvature, gravity, even the laws of physics as we know them. They all emerge from the entanglement structure on that underlying graph. How tangled up things are dictates the geometry. This emergence is governed by something called the Qmn-Entanglement Hamiltonian. So entanglement is the key. It's not just some weird quantum quirk, it's actually building space-time.
It's the architect in this view. And then there's the fractal holographic principle. This is the structure that emerges isn't simple. It's self-similar across enormous scales, like a fractal pattern repeating itself, but applied to the universe's structure, from the tiniest scales up to the cosmic horizon. It preserves quantum information across these scales, suggesting a deep interconnectedness.
Okay, conceptually fascinating. But how do you mathematically link entanglement, which is about information probabilities, to curvature, which is pure geometry? That connection, text entanglement entropy, seems like the magic step.
It is the crucial link, yeah. It builds on earlier ideas, like Jacobson's thermodynamic gravity and Berlin's entropic gravity, but aims for a complete field theory. Qmn uses insights from studying quantum fields in curved spaces, particularly black hole thermodynamics and how entanglement entropy behaves.
Right, the Beginstein-Hawking entropy connection.
Exactly. The math suggests that the components of spacetime curvature, like the Rₘ tensor, are directly proportional to the logarithm of the entanglement entropy density in that region.
So, more entanglement in a region means spacetime curves more sharply there. Stronger gravity.
That's the essence of it. It frames gravity as fundamentally thermodynamic, driven by information entropy. Importantly, this framework is designed to still respect the core conservation laws of GR those Bianchi identities must hold.
How? If you're adding a new source.
By defining this new source, the entanglement contribution, in a way that is mathematically guaranteed to be conserved, just like the regular stress energy tensor dimension, it slots right into the Einstein equations as an additional well-behaved source term.
Okay, so if entanglement is a source of gravity, we need the math for it. This leads to the modified Einstein field equations.
Right. We need a rigorous way to account for that missing 95% the effects we call dark matter and dark energy, without just inventing new particles or tweaking constants by hand. Qmn modifies the source side of Einstein's equation.
Remind us of the structure. It looks like this. Gₘₙ plus Lambda plus Qₘₙ is curvature, Tₘₙ is normal matter and energy, and Qₘₙ is the new piece.
Exactly. Qmn is the entanglement correction tensor. It's constructed mathematically from the underlying entanglement structure, and, crucially, it's defined to be conserved.
And the idea is that this tensor accounts for the phenomena we currently attribute to dark matter and dark energy.
Precisely. It bundles those effects into a single, mathematically consistent term derived from quantum information principles. And this Qmn isn't just one thing. It naturally breaks down into three distinct physical components, each tackling a different major problem in cosmology. Let's break them down. First, the biggest scale. Dark energy, the accelerating universe, that crazy cosmological constant problem. That's the alpha term, correct. The alpha term is the thermal curvature component. Think of it as representing the inherent thermal energy of the quantum vacuum itself, the baseline heat of empty space arising from those quantum fluctuations.
And this heat provides the outward push, the acceleration.
Yes, it naturally generates a positive pressure, mimicking the effect of dark energy. But the really clever part is how it addresses that 10-101 problem.
How?
The strength of this term, the coupling constant alpha, isn't just a free parameter you dial in. The theory derives it from fundamental principles, from the thermodynamics of emergent spacetime and how quantum effects scale renormalization group flow.
Right.
The derivation shows alpha should be proportional to fundamental constants like Planck's constant, speed of light, Boltzmann's constant, Newton's g, and interestingly, this specific mathematical number, zeta.
Zeta of 3. Aprí's constant. Why that?
Yeah, Aprí's constant. It pops up naturally in certain quantum field theory calculations related to vacuum energy and particle interactions. The fact that it emerges here in the context of space-time thermodynamics is seen as significant.
So, by deriving alpha from these fundamental constants and zeta, claims it can calculate the actual observed value of cosmic acceleration, taming the 10-to-1 beast.
That's the claim. It turns the cosmological constant from an epic failure of prediction into a calculation rooted in the fundamental structure of the vacuum in thermodynamics. A huge, huge claim.
Okay, that's cosmic acceleration. Now, zoom into galaxies. The beta term is supposed to get rid of particle dark matter. What's the physics behind the information force beta term? The beta term arises from changes in entanglement entropy across space. Specifically, it's proportional to the square of the gradient of the entropy, a novel S2S22, a gradient. So where the entanglement density changes rapidly.
Exactly. Imagine the vacuum is more entangled or informationally dense in one region than another. That difference, that gradient, creates an effective force, an entropic push, as you called it earlier.
And this push mimics the gravitational pull of dark matter halos.
It seems to, yes. In the low acceleration regions, like the outskirts of galaxies where the dark matter effect is most pronounced, this entropic force becomes significant and provides the extra acceleration needed to explain those flat rotation curves without needing any actual dark matter particles.
Now, people have tried modifying gravity before to explain rotation curves, like MOND. How is this different? How does it avoid just being another curve-fitting exercise that might fail on larger scales, like galaxy clusters? That's a critical point. MOND is largely phenomenological. It modifies the law based on observation. Qmn aims to derive the effects from a deeper principle, entanglement entropy. And crucially, it imposes a consistency condition.
The strength of this entropic force, the parameter epsilon-b, isn't arbitrary. It must be linked to a cosmological parameter, specifically the cosmic saturation scale, where Sybil is a redshift. So beta prop to 1K. Why link the galactic effect to a cosmological scale? Because of the baryonic Tully-Fisher relation, BTFR, this is a tight, observed relationship. A galaxy's total baryonic mass, stars and gas, directly predicts its rotation speed. It's remarkably universal across different galaxy types. Particle dark matter theories struggle to explain why it depends only on baryons, right? They have to carefully tune the invisible halos.
Exactly. Qmn argues that because its entropic force is dynamically tied to the cosmic scale, it naturally reproduces the BTFR's universality without needing invisible matter. The relation becomes a direct prediction of the theory, not something you have to force fit afterwards. That's a potentially powerful advantage.
Okay, alpha for dark energy, beta for dark matter effects. What about the third piece, the gamma term? Quantum noise and texture.
The gamma term captures the finer details, the sort of residual effects of the underlying quantum structure of spacetime. It incorporates things like spacetime torsion, a kind of twisting of the spacetime fabric that standard GR usually assumes is zero.
Torsion, like
Yeah.
spacetime can be twisted as well as curved.
Yeah. And this term is directly connected to that fractal holographic principle we mentioned earlier. It reflects the inherent graininess or complexity of spacetime at the smallest scales.
And this fractal idea, it suggests spacetime isn't just 4D.
The theory proposes that the effective fractal dimension of spacetime at the quantum level might actually be 9. This isn't necessarily 9 large spatial dimensions, but could arise from, say, 3 large dimensions plus 6 compact, curled-up dimensions, borrowing ideas from string theory. The gamma term represents the measurable, low-energy consequences of this complex, possibly fractal underlying texture. It's about the noise generated by the universe's quantum substrate. Okay, it's a compelling, unified picture, but theories live or die by their predictions. Qm's strength seems built for testing, with these 3 pillars across different scales. Let's start with Pillar 1, cosmology, specifically fixing that Hubble tension. Pillar 1 is all about resolving the Hubble tension using alpha-gas. The key prediction isn't just that the alpha term provides acceleration, but that its strength isn't constant. It must be a function that depends on scale, wave number $, and time. Redshift.
Why does it need to vary with scale and time?
To bridge the gap. To solve the Hubble tension, you need gravity, or the effective energy density, to behave slightly differently in the early universe compared to the late universe. Alpha KZ needs to be small enough early on not to mess up the fantastic agreement we have with the CMB data.
Right, preserve the standard model success there.
But then it needs to evolve, to become more significant at later times and on large scales, effectively changing the expansion rate just enough to make the early universe CMB measurements and the late universe distance ladder measurements agree on H2 $.
So the specific prediction is the shape of this function. How do you test that shape?
It requires a massive effort, a joint analysis combining data from practically every major cosmological probe we have. You need gravitational waves from Lake of Virga. They provide standard sirens for independent distance measurements. You need large-scale structure data galaxy surveys like DSI, Euclid, Rubin Observatory mapping the cosmic web.
And the CMB itself.
Absolutely. Planck data, especially the detailed structure of the acoustic peaks and the maps of gravitational lensing of the CMB light, you have to show that one specific alpha K function, derived from the Qmc framework, can simultaneously fit all these diverse data sets and make the H$ values consistent.
And it has to predict specific effects, like the integrated Sachs-Wolf effect.
Yes, exactly. The ISW effect, which is how CMB photons gain or lose energy crossing changing gravitational potentials over cosmic time, is very sensitive to late-time gravity modifications. Qmn nodes must correctly predict the observed ISW signal. Success here would be huge validation for its cosmic picture.
Okay, Pillar 2 jumps from the cosmic scale right down to the lab, detecting the Unruh effect.
Detecting the Unruh effect in the lab. This tests the core thermal vacuum idea. If spacetime is emergent and thermodynamic, as Qmn claims, then phenomena related to vacuum energy and acceleration should behave in a specific, calculable way.
The Unruh effect being, if you accelerate through vacuum, you should feel heat.
Essentially, yes. An accelerating observer perceives the quantum vacuum not as empty, but as a thermal bath of particles, with a temperature proportional to the acceleration. It connects acceleration directly to thermodynamics.
Weird. And this relates to other vacuum effects.
It's closely linked to the dynamical Casimir effect, DCE, where you can shake real particles out of the vacuum by rapidly changing boundary conditions, like moving mirrors very fast. Qmn makes specific predictions for the parameters governing these effects, tying them back to its fundamental constants, especially those related to alpha.
And the experiment aiming for this is LUXE.
Yes, the LUXE experiment at DE-SWI uses high-intensity lasers and electron beams to create extreme conditions, essentially simulating very high accelerations to try and detect the faint thermal radiation predicted by the Unruh effect or related phenomena.
Okay, but the sources mention a problem here. Attention.
They do. Early comparisons between the Qmn prediction for the Unruh signal expected in LUXE's Phase 1 and the experimental constraints seem to show a mismatch. The prediction is reportedly off by 2 orders of magnitude.
2 orders of magnitude. That sounds bad. Usually that might kill a theory.
In many contexts, yes. But Qmn is built with a kind of self-correction mechanism, this hierarchical protocol. It doesn't necessarily view this tension as immediate falsification.
How does that work?
The protocol requires that if data from one scale, like the lab, conflicts with the current parameters, the theory must adjust its scale-dependent functions, alpha betas linked to new killers, in a way that maintains consistency across all scales. So a tweak forced by the lab data must still allow the theory to fit the galactic data, pillar 3, and the cosmological data, pillar 1.
Ah, so it's not about arbitrary tweaking. A failure here puts constraints on the entire framework across all scales.
Exactly. It forces a systematic refinement, testing the theory's robustness and interconnectedness. It's designed to iterate towards a better fit based on data, rather than collapsing at the first hurdle. It's a test of the framework's resilience. Okay, interesting approach. Finally, pillar 3 takes us back to galaxies, getting rid of dark matter for good.
Galactic rotation consistency. This is about nailing the prediction from the beta term. It's not enough to qualitatively mimic dark matter. The entropic acceleration must quantitatively predict the rotation curves of a wide variety of galaxies using only their visible baryonic mass.
Stars and gas, nothing else.
Nothing else needed. This requires going beyond just fitting existing galaxy data. It demands extremely precise measurements, especially in those very low acceleration environments where the predicted entropic force takes over from standard gravity.
Like measuring the exact point where gravity seems to transition.
Precisely. We need detailed gravitational maps and acceleration profiles from regions where $8 is the characteristic acceleration scale related to MAOND and also predicted within Qmn.
And the target precision for this test sounds ambitious for astronomy.
It's incredibly stringent. The sources state a target deviation of less than 0.1% between the acceleration predicted by the theory, calibrated on galactic data, and independent high-precision measurements, potentially made using test vehicles or probes in controlled, low-acceleration environments within our solar system or beyond.
Wait, comparing galaxy scale effects 1020 to vehicle scale measurements, that's 23 orders of magnitude in scale.
That's the audacity of the prediction. If the beta term, rooted in entanglement gradients and linked consistently to the cosmic scale via Qpei scale, can maintain that 0.1% accuracy across such a vast range of scales, well, that would be incredibly compelling evidence that entropic force is the reality and particle dark matter is unnecessary. It would fundamentally rewrite galactic dynamics.
Okay, let's just imagine for a second. Imagine Qmn passes these tests. Pillar 1 resolves Hubble. Pillar 2 sees the Unruh effect correctly. Pillar 3 nails galaxy rotation curves. What does that mean? Gravity is thermodynamic, informational. What does that let us do? It changes everything. If gravity emerges from the quantum information state of the vacuum, and we understand the rules governing that emergence, then theoretically we can interact with it, control it. This opens the door to the theory's ultimate, perhaps far future goal, metric engineering, actively manipulating the geometry of space-time itself.
Exactly. Not just being subject to gravity, but potentially generating or shaping gravitational fields locally, creating specific space-time curvatures on demand.
Okay, sci-fi territory maybe, but what kind of technology does the theory envision could even approach that? It sounds like you'd need incredible quantum control.
You absolutely would. It hinges on achieving and controlling macroscopic quantum coherence on an unprecedented scale. The sources mention 2 key technological concepts. First, using Bose-Einstein condensates, BECs, in triple well potentials.
BECs, those ultra-cold clouds of atoms that act like one giant quantum wave.
Precisely. They are exquisitely sensitive quantum sensors. The idea is to use BECs trapped in these carefully designed triple well potentials, not just to sense the background spacetime metric with incredible precision, including the tiny effects predicted by the gamma term, like torsion or graininess, but potentially as part of a feedback loop for control. They're the feelers, the sensors of the local gravitational weather.
Okay, sensors. But what provides the muscle to actually engineer the metric?
That's where the proposed central toroidal superfluid reactor comes in. This concept is, well, highly advanced. It involves a composite material, specifically a mixture of helium-3 and mercury-196, He3Hd196.
Why that specific mix?
Because this combination is predicted to have unique superfluid properties at achievable temperatures. Superfluids flow without any viscosity, allowing for quantum effects to manifest on a larger scale.
And the goal with this superfluid?
The key is that under the right conditions, rotation, magnetic fields, this superfluid composite could potentially host a stable magnetic vortex lattice. This lattice structure, a kind of ordered pattern of swirling quantum vortices within the superfluid, is theorized to be the necessary medium to achieve and sustain the large-scale, coherent quantum state needed to actually interact with and modify the space-time metric derived from the vacuum's entanglement structure.
So the BEC's sense, the superfluid vortex lattice X. This sounds like the physics basis for advanced propulsion or field generation concepts like the rumored TR3B.
The framework explicitly aims to provide the theoretical underpinning for such advanced gravitational control vehicles. Whether those specific historical rumors have any basis is separate, but Qm's aims to show how such technology could be physically possible if gravity is indeed emergent and controllable via quantum coherence.
The whole paradigm shifts then. We're not just trying to find dark particles to patch holes in GR, we're potentially learning the operating system of the universe.
That's a great way to put it. We'd move from being purely observers, cataloging phenomena, to potentially becoming engineers. The theory provides the fundamental parameters, alpha, beta, derived from nature's thermodynamic and informational architecture, supposedly giving us the handles to interact with gravity itself. Hashtag tag outro.
So we've gone from this deep crisis in physics, GR and QM refusing to connect, forcing us into a dark universe model, to this really audacious proposal. Qmn-O. Gravity isn't fundamental, it emerges from quantum entanglement. And it comes with a specific mathematical tool, the Qmn-O, which breaks down neatly, the alpha term for cosmic acceleration, tackling the Hubble tension.
The Gₘₙ term generating an entropic force to replace dark matter, testable in galaxies.
And the whole thermal vacuum idea being probed in the lab via the Unruh effect. 3 pillars, 3 massive tests.
And if it holds up, if we confirm that gravity is informational and controllable through things like superfluid vortex lattices.
The implication is just staggering. Are we moving beyond physics as observation towards cosmic programming, actually engineering space-time?
It definitely leaves you with that provocative thought. If space-time is fundamentally information, and we learn how to manipulate that information, what does that do to our concepts of cause and effect, of geometry itself? If reality's code is accessible, what are the limits?
A truly mind-expanding deep dive today. If this has sparked your interest, you should definitely look into entanglement, entropy, and cosmology, and also the history and importance of the baryonic-Tully-Fisher relation. It's key context for understanding these alternative gravity ideas.
Absolutely.
Thank you for joining us on the deep dive. We'll catch you next time.